Good morning, everyone. My name is 𝗬𝗎𝗓𝗦𝗓𝗡. Thank you very much for attending uh, Catch Me If You Can, the frequency response of a PID controller. It's going to be a bit of an in-depth kind of webinar, so I appreciate any kind of feedback, and there'll be a Q&A at the end. We'll talk about that later on. So thank you very much for attending, and I'm going to turn the camera off because it's way too distracting. As you can see, there's a QR code. We've switched at Lakeside to digital business cards, so you can take your smartphone out and upload. It takes you to Haystack, I believe, and you'll be able to upload my business card. And this QR code is going to appear a few times throughout this webinar. So if you don't have your tracking device, I mean cell phone, with you, your microphones are off. We are in a webcast mode. So at the end, there will be a Q&A, and you could type in through the Q&A box or the chat box. It doesn't matter. And then, so just to be able to answer any questions at the end. Actually, at the end, we'll also be putting out a poll. So if I just go back to here, make sure that, no, do this one here. There will be a poll as well appearing. So if you could just fill that out. It's just it's talking about virtual training versus in-person training. We're trying to figure out my next step, especially in the fall. There is a 10-second time delay from the moment I speak and the moment you hear me. Again, that's because of webcast mode, and therefore get a better streaming experience. But if you think that if light travels at 300,000 kilometers a second, that actually means that I'm 3 million kilometers away. I actually met up with this guy called Bob Lazar, and he used to work at Area 51, and he hooked me up with this slightly used flying saucer that he had in his garage. It only has like 5 quintillion kilometers on it, and he taught me up with a little bit of element 115. So that's where I am. I'm 3 million kilometers away from the planet Earth right now. Your questions are anonymous, so only I can see it. So that, don't be shy. I really encourage questions. I think it's great to see the level of involvement here, and you will also always be able to again to be able to reach me. Again, there's a QR code. Maybe I'll get rid of that arrow there, and the QR code again, so you can scan and be able to get in touch with me that way. This is part of a series of webinars I started last year. So this is my 12th webinar right now. If you missed some of the previous ones, you can actually, there's a sticky note available on the platform, and you can access, you got to sign up to Big Marker, and then you can access actually all the webinars, not just mine, but mine are better, but all the webinars out there. Yes, obviously this session is being recorded as well, and you will be emailed a link to the recording after this webinar is over, probably later today or tomorrow. A little bit of a safety moment. I know we just passed the spring equinox, and it's always a good time to change our batteries in our smoke detectors and carbon monoxide detectors. Very, very important. As a matter of fact, I had to replace one actually, I think it was last spring, actually, because it actually had expired. So we had to replace all the carbon monoxide detectors on all the floors in my house. But obviously, some of the signs of carbon monoxide, since it's odorless and tasteless, headaches, nausea, obviously, hopefully, we do not go into the latter stages of that. Uh, Obviously, be careful. We're coming up to nicer weather, barbecuing, charcoal. I love charcoal barbecues. So if you do, be careful if you do that in the garage. Make sure it's properly ventilated, make closer to the door, and so forth. A little bit about Lakeside. We actually have facilities. Obviously, head office is in Mississauga. We have offices in Sudbury, Sarnia, and Dundas, Ontario, which is near and between Hamilton and Mississauga. We have a brand new kind of a fabrication location there. We just acquired that last fall, so we're pretty excited about it. And so a lot of our fabrication, a lot of our sanitary fabrication skids. We also have taken over valve servicing which was previously done by Fisher Life Cycles and now, or Emerson Life Cycles, which is now, we actually, Lakeside will be doing that at that facility. We'll be servicing all the control valves with the exception of nuclear control valves. Other offices, Port Elgin, Thunder Bay, and Winnipeg, and I've pretty much worked in all of these industries here. We're part of the Emerson Partner Network, Impact Partner. There's 21 of them, as you can see. Our territory starts just from this side of the town of Kingston, to the Manitoba-Saskatchewan border and a little bit of Nunavut. And you can see that to the west is Spark Controls, and to the east is Laurentide Controls. And why do we go this way? It's to be able to. I think Emerson kind of thought way back when, and was to have a better. It's better to have a local presence than having a larger monolithic corporate presence, and it's better to serve you. And we do sell a lot of stuff. This is not my favorite slide here, but in the handout section, you can download our product line and you can see everything that we actually sell and service. And the whole idea here is to provide you with a positive customer experience. I always say any experience, any feedback is good feedback. And we are striving to provide you with a positive customer experience when you interface with Lakeside. So again, any feedback is good feedback. So please go ahead and provide the feedback that you think we deserve. A little bit about myself. Yes, that's the same picture on my digital business card. I kind of look like Billy Idol's uglier younger brother or older brother, I'm not sure. So I do a lot of control loop tuning, troubleshooting, assessment, data analysis. Looking at doing some work in the recycled paper mill plant, hopefully in the next couple of weeks. And also cooling tower controls at a chemical plant. So we do a lot of that. Go to site. I'm responsible for advanced controls, model predictive controls, neural net application. Do also DCS alarm metrics. I'm sure some of you who are in operations right now, if you actually go to your control room, you look at your alarm page, I would bet you some good dollars there that the alarm page is probably full of nuisance alarms. So we do alarm analysis and alarm metrics, and the idea here is to make sure that your alarms are relevant. We're not there to eliminate alarms. We're there to make them relevant. So therefore, the operator needs to take an action on that. I do have a couple of gentlemen. Actually, Andrew Poyton is my supervisor now. He helps me out a fair bit once in a while. And Dean, who just got promoted. Congratulations, Dean. He's actually a project leader. He helps me out once in a while as well. So feel free to reach out to them as well. And I do offer training courses, basic instrumentation for operation. I just taught this course last Tuesday. The next session is I believe is April 19th, and there's another one in May. Process Control Techniques 1, aka Loop Tuning 1. I'll be teaching that next week. It is actually sold out, so thank you very much for those who enrolled. There will be two more sessions, and one at the end of April and one at the end of May. And I do have a more advanced course, Process Control Techniques 2, which will be offered in September, October timeframe. You must have attended Process Control Techniques 1 before you can sign up for that. And last and not least, I do have blogs that I've put out there. I was trying not to make them too dry of a technical paper. They are a bit technical, but the idea is I put a bit of humor in them, and there's always a moral to the story at the end. So you can go to our website, lakesidecontrols.com, and just do search for Looney Tuner or blogs, and then you should be able to find them. All right, now here's the good stuff. Let's pay attention here. Have a quick drink of water here. So today we're going to cover what is frequency response. We're going to kind of define frequency response, and then we're going to extend on that, and then we're going to talk about low pass and high pass filters. And you'll see, how does that relate to the frequency response of a PID controller? And I hope to make that bridge. So we have to understand low pass filter, high pass filter, and then obviously how does that relate to the frequency response? And then how does that relate to the tuning of the PID controller and how the tuning affects the frequency response of that particular controller? Now, if you remember last webinar, 𝗦𝗧𝗕𝗏𝗦𝗧𝗔𝗬, love saying that, 𝗦𝗧𝗕𝗏𝗦𝗧𝗔𝗬, we talked about power spectrum analysis and how we can use that in control optimization. And so I'm going to review that because we're going to build on that a little bit. So for those of you that did not attend, you can please pay attention. So let's say we have this one cycle here, and then I'm going to add this cycle, and then I'm going to add this cycle at different frequencies. If I add them all up, this is what it would look like. And this is what we call in a time domain. This is obviously, you take a look at it from a data set and the trend and so forth. That is the time domain. However, we can look at it differently. We can look at that signal differently. We can take the power spectrum, a fast Fourier or full Fourier analysis, and that will break down that signal, this signal right here, break it down into fundamental harmonics. 𝗏𝗦𝗧𝗔𝗬 said that pretty much any time series can be reproduced by adding an infinite amount of sine waves and cosine waves of various amplitudes. And so here it'll break it down into various components. You can see the three major harmonics there. One more thing I want to talk about before I get into, when we talk about power spectrum, we can actually display it a few different ways. So there's a typical power spectrum here. Anybody who's done any kind of vibration analysis, reliability, whatever you want to call it these days. So the bottom axis here is in frequency, So it is in cycles per second or hertz. And the faster variability is towards the right side, and the slower variability is on the left side. And you can see here, this is plotted linear versus linear. Linear frequency at the bottom, linear amplitude on the vertical axis. So we're going to be talking about, though, today, log-log plots. Log-log plots, where you could see the x-axis is an equal distance are multiples of 10 of each other. And as is the y-axis is in multiples of 10s. Why do we use log-log plots? Is because we can turn exponential curves, the one we see on the left-hand side, into straight lines on the right-hand side. And that will help us visualize better the frequency response of low pass filters and high pass filters. So what is frequency response? Let's say I'm holding, now I know that looks like a scale there. I actually really wanted to have a spring, but I couldn't find a proper image there. But it just pretend it's a spring. And so what is the frequency response? So I will have a process input. So my hand is going to move up and down, and I will observe how the rock will behave in terms of amplitude. And the ratio of the movement of the rock divided by the amplitude of movement of my hand will determine the frequency response as I vary the frequency or period, whichever way. So interesting because we talk about frequencies and really it is frequencies, but I've mentioned before in my previous webinar, we talk about in the field of process control, we don't deal with hertz, we deal with seconds or minutes per cycle, which would be millihertz and microhertz. It just sounds better when we talk about 15 seconds, 15 minutes per cycle, as opposed to almost 1 millihertz. So if I were to now change move that system up and down. So my hand is basically going up and down like the white line, and I would observe the movement of the rock. If I do it slow enough, they seem to track each other pretty well. So now we have a ratio of 1 in terms of amplitude. Now, if I change it a little bit faster, the rock is still tracking the movement of the hand, same amplitude, looking pretty good, still a ratio 1. A little bit faster, still pretty good, still tracking the movements of the hand in terms of amplitude. Now, this is interesting. Now, you can see here, I'm moving a little faster now, but now it appears that the amplitude of the rock seems to be greater than the amplitude of my hand movement. And so now it appears to be the ratio would be greater than 1. And if I go a little bit faster, now you can see here the actual rock, the amplitude of the rock wave, that sounds pretty cool, is much larger than the amplitude of my hand. So now we have a ratio much greater than 1. That means now, essentially at this point, what's happening is that we're hitting a resonant frequency of the system. The system is actually second order underdamped response, and we're hitting a natural resonant frequency. Now, if I keep going any faster, now you can see the hand movement is going really, really fast, but now the rock is no longer able to keep track in terms of amplitude, the changes affected by the hand, and therefore the amplitude ratio is much less than 1. We're falling down. So therefore the system is attenuating the input signal. Okay? Let's talk about filters, low pass filters and high pass filters. Some of you may or may not recognize this. Some of you may have little flashbacks of nightmare. This is an electrical circuit, and I have a resistor and a capacitor. This is known as a low pass filter. So let's look at it from 2 different points of views. Let's look at it from the time domain point of view. If I were to put a step change on the input voltage, what would I observe at the output voltage? I would observe a first order response. A first order response. Very, very similar to what those of you who've done tuning or watched me do tuning or taken my course. The first step that we do before we do any tuning is that we do a bump test to measure the process dynamics. So this is completely the same. Now let's look at it from the frequency response. And yes, the time constant of that response, tau, is the RC, the value of the resistance times the value of the capacitor. Now let's look at it from a frequency response point of view. So if I were to put some sort of signal generator at the input voltage in, and I was able to vary the frequency, I would observe different amplitudes at the output. In this case, you could see the frequency is pretty high, and what's happening is that the low pass filter is attenuating the input signal. It is attenuating. And hence the name of low pass filter means is that it will pass after a certain point and slower variability, it will pass that through. The ratio amplitude will be pretty much 1. But then the faster and faster the variability will be, the more and more it gets attenuated. And note my word attenuated, not eliminated, attenuated. It gets squished. And the cutoff period of this low pass filter is equal to 2 pi tau. And why the 2 pi? because it's more than 1 pi? No, that's how we convert the time into radians per second. So let's talk about low pass again. Now, suppose now I were to actually pass a signal called white noise as the input, voltage input. White noise, those of you have attended I believe my 4th webinar, is it noise or is it music? We talk about white noise, is characterized by having equal amplitude across the log-log plot, as the red white line indicates. And so it's obviously it's like a white light. White light is actually we seeing all the colors in the visible spectrum at the same time, which we perceive as white. So it's the same idea. Now we pass that through a low pass filter, and what obviously the low pass filter will do is that it's going to take out the higher frequency component of that white noise. It will no longer be white noise and pass through the slower components. If I were to take a look at the power spectrum, the log-log power spectrum, you can see the higher frequencies now are being attenuated, And if I were to put numbers on there, if my tau value is 5 seconds, the cutoff period is 31.4 seconds per cycle. And then here, since the x-axis is in hertz or cycles per second, that corresponds to 0.0318 hertz. So what does that mean? It means that any frequency component from this side over gets squished down. Yes, that's a technical term, gets attenuated. And right at the cutoff period, about 30% of the variability gets attenuated. After 10 times faster than that, so if I were to look at this, we'll talk about this later on, but at variability at 3.14 seconds, 90% of the variability will be attenuated. I'll talk about that a little bit more later on. So now let's talk about a high pass filter. And the high pass filter is essentially you just switch the positions of the capacitor and the resistor. And once again, if I put white noise through there, it's going to pass through high frequency components of the white noise and attenuate the lower frequencies. So you're wondering again, why do I need to do this? I went through the nightmare in university or college trying to forget all this. I'm going to relate this in a minute. So just to recap, a low pass filter attenuates high frequencies, and a high pass filter attenuates low frequencies. So remember I talked about the cutoff period, and we're going to talk about now for a high pass filter. So once again, for a high pass filter, the cutoff period in this example is 31.4 seconds per cycle, or 0.013 hertz. Now remember, our control loops are bombarded by all sorts. It's not necessarily going to be white noise, but it is bombarded by variability that it can be from very, very slow type of variability to be seconds, minutes per cycle, hours per cycle, days per cycle, seasonality, months per cycle, if you want to go all the way that far. But what does this mean in terms of cutoff period and attenuation? It means that variability that is 10 times slower, variability at 314 seconds per cycle, 90% of that will be attenuated by the high pass filter. 90%. So if you think 90% at 31 points, that's over what, 5 minutes per cycle. 5 minutes per cycle. 10% still makes it through. That's the key concept I want you to actually get. So let's relate this now to PID and tuning. So when a controller is in automatic mode, it has specific numbers in tuning. The process obviously has its own dynamics, so we must consider this together. Depending on how we tune it, we can tune it to be having overshoot. So it has a bit of overshoot and undershoot. That's known as quarter amplitude decay. It is an underdamp response, similar to the spring in the hand and the rock. Or we can tune it more like a first order response, more like the RC circuit following a set point change. So you can see here, this is the total sum of the PID and the process together. That is now one system. And now we can take a look at that one system and see how does that, what is the frequency response of that total system. So let's say if I tune this with a lambda value of 15 seconds, that is known as the closed loop time constant. All that means is a fancy word that means closed loop means in automatic. That's all it means. That means then that the cutoff period will be 94.2 seconds per cycle, or 0.0106 hertz. That means that variability that lives at 942 seconds per cycle, 15.7 minutes per cycle, 10% of that variability at that frequency will pass through. It's quite amazing. It's kind of a little bit hard to kind of grasp that, but it's very true. 15 minutes is a long time. So how are we going to do this? So this is the model that I developed here. So I got my PID block here. I have a dead time. I built a bit of dead time, about 5 seconds dead time, if I'm not mistaken. I got two time constant, one that kind of models the dynamics of the valve, one that models the dynamics of the process. And right here, this is a signal generator. I'm going to be adding here some variability onto my PV. But before I continue here, I want you to understand we can look at this system from 2 points of view. So we could look at it from a load rejection point of view. What are we inputting here and what are we measuring over here? We can also look at it from a set point change point of view. So if I were to input this sine wave into the set point and vary this, actually, let me change that right now. So actually vary the set point very slowly, the PV would have no problems keeping track of the demands of the PID controller. There would be a ratio amplitude of around 1. And if I were to vary the set point very quickly, then the amplitude of the PV would be a lot less because it will have a hard time keeping up with the demands, the fast changing demand of the set point. My point here, from a set point change point of view, from a set point change, is going to be a low pass filter, meaning slow set point changes will be tracked, fast set point changes will not be tracked so well. But I'm interested now in the load rejection aspect of the PID controller. So what I'm going to do is that I'm going to change the period of that amplitude, the period of that cycle, add that to my signal, and then observe how well does my PID controller reject the varying frequencies load disturbances. So if I were to do, this is known as a high pass filter. So from a load rejection point of view, a PID acts as a high pass filter. What does this mean? It means that if the variability is very, very, very slow, I have no problems controlling that out. But as the variability starts to increase in frequency, I'm getting less and less able to actually attenuate it to a point where I will have no chance of attenuating and the variability will pass through. So this is what I did here. I tuned this controller and I put it through a cycle of 2,700 seconds per cycle. This is actually all on the same time scale, all on the same Y scale. So here I measured this, I had a ratio of 0.05. That means that the cycle here was well attenuated. So maybe I should go back to here and explain this a bit more before I do that. So what I have here, this is the actual disturbance I'm injecting. The blue line you see is the output command of the PID block. The white line you see is the set point, and the very squished yellow line is the PV. So here we are at 2,400 seconds per cycle. And what's happening here is pretty much the same ratio, 0.05. That means 95% is being attenuated. And now 1,800 seconds per cycle, 6.5% is remaining. 1,500 seconds per cycle, ratio keeps going up. That means more and more is passing through. An amplitude ratio of 0.09. 1,200 seconds per cycle, amplitude ratio of 0.105. So we're getting near, obviously, at the 90% part. 900 seconds per cycle, 0.135. 600 seconds per cycle. You can see the trend going on here. The faster, now 20% is making it through. 500 seconds per cycle, 24.5% is actually making it through. 400 seconds per cycle, 0.3. 300 seconds per cycle, almost 40% is making it through now. The PID controller is having a very difficult time trying to attenuate that cycle. 250 seconds per cycle, 0.465. 0.565 or 56 seconds for 200 seconds. 150 seconds, 0.71. Now we're reaching the cutoff point, but something kind of interesting is going to happen here. So 100 seconds, 92.5. That means it's only attenuating 7.5%. Now, 50 seconds per cycle, this is interesting. Now, the ratio is actually greater than 1. That means now the PID controller is actually amplifying that cycle by a factor of 26.5%, amplifying it. And the reason for that, and I'll get to this maybe a little bit later, but the reason for this is that even though I tuned it as a first order kind of response, I lambda tune it, any processes that have any kind of dead time will have some sort of natural resonance, no matter how you tune it. And this is what I wanted to show you here. And so this is the actual frequency response. I plotted all those numbers. Now this is linear period on the x-axis and linear amplitude on the y-axis. And you can see here, this is where that resonance was actually occurring. Now, if I plot that log, we could see our familiar curve that we had before. And if I were to continue here, this would probably go straight like that. And we got our minus 20 decibels per decade going here. And here is that resonance we were talking about. So I got a bit of a demo going on here. So just so you kind of see it in action, it's always a bit more interesting. So this is the Lunch and Learn 12. So I got here, I can actually change the amplitude. I'll leave the amplitude the same. And there it is at 10 seconds per cycle. And I started off where the, actually probably have a better, I think I have a better one here. Bear with me. Lunch and Learn signal generator, yeah. So there we go. So you can see here, there's the amplitude of the sine waves. There's a bit of attenuation going on. So this cycle is around, if I remember, 120 seconds per cycle. And I changed the frequency here. And you can see that it's actually a little bit higher. The yellow line is a little bit higher in amplitude than the orange line, which is the disturbance I'm putting in there. And then what happened is I changed it to 10 seconds per cycle. And you can see that there's no change. There's a variability is completely passing through. The variability, the amplitude ratio is 1. So I just wanted to show you. So if I were to actually go to the end here, and what I can do is just change this to something very slow. I get back to 120. I'm not going to spend all day just watching in here, but you'll find that the PID will have an easier time controlling out that slower frequency. And you can see already where the orange line, the amplitude of the orange line is higher than that of the yellow line because the PID is controlling that out. Okay, so what does this all mean? What does this all mean? Well, first message is that, if PID is not magical. It can control, but its capabilities are quite limited. And is based on the tuning. As a matter of fact, I just showed you, especially with processes, depending on how you tune it. If you tune a PID controller in an underdamped fashion, meaning there's set point overshoot and undershoot and overshoot and undershoot, it will have a significant resonant peak where it will actually amplify part of that variability. It's a little bit like driving a car with bad shock absorbers on a very bumpy road. And I'm sure right now, springtime, they're all pretty bumpy. So the car would tend to resonate at a particular frequency. If you lambda tune it, that resonance is not as great. But if your process has dead time, it will resonate a little bit. But if you think that our process is subjected to all sorts of variability, as I'm displaying it here, a lot of times it's actually being bombarded more by slow variability. So slow variability, and that's characterized by kind of the slow drifting of that signal. And superimposed on top of that, there's a bit of noise there, and that kind of be appeared here. It doesn't really show up that much, but it's actually there. And what does it mean? It means that most of your variability is actually slow. And if I were to tune it properly, because now my PID controller is now a high pass filter, it will attenuate some of the slower variability and reduce process variability that way. That is what it means. So I hope I conveyed the message clearly that we not only must think of PID performance in the time domain, we must also think about it in the frequency domain as well. So I'll put up here for questions. And I know that I do have one question already here. So question is, what is the software you use to build your simulations? Thank you very much. It's Raphael. It's actually, I use our control platform called 𝗪𝗘𝗦𝗧𝗑. This is our the Emerson platform that we, as Lakeside and all the Emerson Impact Partners rep. It's called 𝗪𝗘𝗦 control, distributed control system. So another question here. If you had a disturbance that was sinusoidal and you cannot get rid of the disturbance, would you change your tuning to be different from a typical set point tuning to attenuate specifically the sinusoidal disturbance? What I think you're asking there, Dean, is that if I have a sinusoidal disturbance coming into my process, whatever, maybe it's some sort of slow rotary piece of equipment, to effectively attenuate that cyclical disturbance, you would have to tune it such that the cutoff period of your PID controller is 10 times faster than that of the cyclical disturbance. Now, depending upon the period of that cyclical disturbance, it may or may not be able to tune our PID controller to be 10 times faster than that. So that's something to consider. Good question, Dean. Is there a case where you tune to protect against sinusoidal disturbance instead of for a good set point response? I guess what you're trying to ask there is that there's two ways you can look at tuning. You can look at it from a set point change point of view, which a lot of us kind of do. It's also known as the servo response. But we also can look at it from the regulatory response, meaning the set point is fixed and how well does it attenuate the variability that the PID controller is experiencing. And so therefore, therefore sometimes we may want to analyze the variability. So let me take a look here. We may want to analyze this variability right here. And that can tell us, well, maybe we just need to tune it to attenuate the significant portions of the variability out and not concern ourselves so much with the set point response. So it depends on how you want your controller to respond. So another question, how do you mitigate the amplification of the process with a dead time process close to the resonant area? Unfortunately, there's nothing much you can do. As a matter of fact, even if you try to use a dead time compensator, and I think it was my webinar number 10, I believe, where I talk about modified Smith predictor, it still will resonate because of the dead time. And again, it depends on the degree and the amplitude amplification will depend on how the response is and how kind of close to second order it is. But there's no way you can actually attenuate. It will resonate no matter what. Now, there we go. We always have that question about derivative. Always my favorite. For those of you who don't know, D stands for don't. D stands for doom. D stands for disaster. But I always appreciate the I always appreciate questions about derivative. Would derivative action help in these situations? And do you recommend the use of derivative action? I kind of answered that second part of the question a little bit for you. Um, I'm going to give you the kind of the lawyer answer there. It depends. Uh, where perhaps derivative may help. It depends on the overall um, the overall system response, but it probably will just mitigate it, but not completely eliminate it. Another question: is there any phase shift analysis, frequency response, and performance? Do we consider phase shift analysis? Yes, there is a phase shift. I did not address it here. Here I was dealing with amplitude ratios. So you heard me talk about 20 decibels, minus 20 decibels per decade. So I talk about that. Power decibels would be 10 decibels per decade. But yeah, there is a phase shift component as well, especially when you hit the resonant frequency. There is a 180-degree phase shift, so which makes it come in phase at that particular. It makes things. That's why it amplifies uh, the output versus the input amplitude. These are great questions. So I'll just going to pause here a bit more, see if there's any more questions. And as I said here, you can always contact me. You can always contact me if you think of other questions. So I'll give another minute or so. Incidentally, like I said, you can click on that link in the sticky notes, and you get access. You got to sign up to Big Marker, and we'll ask you a whole bunch of personal questions. No, just kidding. Just your shoe size. But there you can actually access not just all my previous webinars, but all the other webinars as well. So you could do that. Um, I will be having more webinars in the future. I haven't decided on additional subjects. So perhaps you can if you want to, you can actually give me some ideas. I just put out a poll. Actually, incidentally, I should have put it out at the beginning of the Q&A. This is just to figure out. I'll be doing some. I'm coming into the end of my training season. Usually in the springtime, I finish my training in at the end of May. I don't provide training courses June, July, or August. That will restart in September. Just try to get a feel as to how you people feel about virtual training versus in-person training. In-person training is there's always visual cues that we get. There's probably some intangible benefits that we get from in-person training. But at the same time, virtual training is certainly more convenient. We don't have to go anywhere. You can actually attend virtual training without traveling, and in the comfort of your sweatpants and pajamas and slippers. So I have another question here. That I remember the cutoff is when the signal is attenuated at 3 decibels. You are correct. Actually, minus 3 decibels. That is correct. And so what happens there is that so if you take uh, minus 3 divided by 20 and you take the inverse log of that, you will get a ratio of 0.707. That means at the cutoff period, just under 30% of that variability is attenuated. 70% passes through. So you guys are doing great. Obviously, thank you very much for asking that. So far on the poll here, it says I prefer the convenience virtual training over in person. In virtual is winning. I'm 44% prefer virtual training, 26%, 75%, and so forth, and only 3% gave me a 0% in terms of that's what I prefer, virtual training. Interesting. So like I said, I'm going to pause a bit longer here. I want to make sure that I answer all your questions. All right. Well, we're coming up to 10 minutes to the hour. 10 minutes to noon here in, well, I'm not on planet Earth. I'm in my secondhand flying saucer. But for where you guys are, probably 10 minutes to the hour. I certainly want to thank you very much. I will, like I said, I haven't determined any additional subjects. I hope to be able to put another webinar together, possibly the month of May. I will keep you posted. You can always visit our webpage, 𝗦𝗧𝗔𝗬.com/events, course and events, and usually it'll be posted there. But we'll make sure that we push out that notifications. So unless there's any more questions, I certainly want to thank you all for attending. Really appreciate it, and I hope you found this informative. And be safe. Watch out for your carbon monoxide, and obviously keep on watch out for yourselves out there. Thank you very much, and hopefully one day we'll be able to see you in person. Thank you very much.